Okay, in the previous lecture, we had actually had looked at Carnot's approximation for a 3-stage closed network, basically estimating the blocking probability. Before now we move forward, I would like to introduce another small concept which we call as time switch. Okay. So far when I was talking about a switch, I was always drawing a figure something like this, and I always said a telephone is connected here, a telephone is connected here, there is an input port, there is a telephone connected on this side or trunk lines, and only one voice communication can happen here. We call it a circuit actually. Okay. But as we all know, this is fine if it is analog telephony, because analog signals can pass through separate wires. But this actually analog communication is not that much lucrative. People have moved on to digital communication. So reason being, what basically is the difference is, if I have put a time axis here and I would like to measure the voltage which is representing the signal, analog will be something like this. So in fact, when I want to actually excite a speaker, signal, the voice signal which is actually put, amplified voice signal into the speaker, is something which is varying in this fashion, because of which diaphragm moves back and forth and we listen to the audio. But this can actually, when we transmit this kind of thing over a communication channel, this gets corrupted and you cannot remove the noise just keeps on adding, keeps on accumulating. So people moved on to something called a digital signals. Advantage of digital signal is that when I am transmitting, I can actually multiplex or put many voice channels together on one single wire. That is one advantage. Secondly, I am not representing my voice in this analog waveform. I represent it, I in fact do two things here. First of all, in fact, if I draw the spectrum, this is a random process, and if I draw the spectrum, power spectral density, mostly it will be something like this. And for human voice communication till 4 kilohertz, I have drawn it in bidirectional, this is 0. So negative and positive both I have drawn. So this is actually good enough. So roughly it is 50 to 3.6 kilohertz, that is a band, and then there is a guard band, so that if I want to do frequency division multiplexing, transmit something else, so this much guard band does exist. So in fact, most of the communication devices will capture your voice and will band limit it to 3.6 kilohertz. We call it 4 kilohertz actually, that is a last one. And of course, now this we can transmit in digital format, but how? So first thing which we have to do is, we have to do the sampling. So if any signal which is in baseband is till 4 kilohertz, I need to sample at twice the higher rate, so which actually means 8 kilohertz. So 8 kilo samples per second, so I will create a signal which will be something like this. If this was the baseband signal, this was the baseband signal, this one. This is the replicas which will get created when I will do sampling, and I can always filter it out by using a low pass filter, get back my original signal. So this frequency twice the maximum 2 FM. So frequency of sampling should be equal to 2, should be greater than 2 FM. This is what is known as Nyquist frequency. Okay. So if I sample at more than this rate, that is good enough, I can always recover back my original analog signal. So in fact, most of the voice in all telephones, they are being sampled because of this reason at 8 kilo samples per second. But once you do that, the voice will look something like this. This thing is gone. These are sample values which I have. So, I have got the samples, and the envelope of this will tell me what the signal is, and I will be able to play it back. This can be done using low pass filtering. We do one more thing, but remember this is still analog, my variation is continuous, and because of which if noise corrupts this level, I will not be able to figure out how much was the noise and how much was the signal. So, we also do something called quantization. This is a discretization in time. I can do discretization in amplitude also. So, normally for telephony systems what we do is we define the range. So, 0 volt to say 5 volt is the range signal. So, we will divide this whole thing into 256 levels. So, if you are in the first level, or you can be in second, you can be third. So, I will just need to remember in which level you are. So, any value which is within this range will be represented by this level. So, since I have only 256 levels, I require only 8 bits to represent a level, to identify a level. So, for each one of them I will quantify, identify the level, and will find out what is the 8 bit representation for that. So, for each one of these samples now can be discretized in amplitude and then represented by 8 bits. So, I will be now sending 8 bits for every sample, and a bit means actually 1 and 0 kind of combination. So, 1010 sequence, some number, it is 8 bit number which I will be sending for each sample. And now the number of samples, it means what is the period between these two? 8 close samples per second represents, if I want to find out 8000 samples per second. So, I can actually do it 10 to the power 6 microsecond by 8000. So, which will be 10 to the power 3 by 8, which turns out to be 125 microseconds. So, every 125 microsecond, 1 octet, we call it, we do not call it byte in telecom world, we call it octet, 1 octet will be transmitted. And once you do that, I end up in actually 8 bits into 8 kilo samples per second, or 8000 samples per second. So, these many bits per second, which is 64 kbps. So, most of the voice telephony circuits are 64 kbps digital circuits. So, once we know that, now we are actually doing digital switching. Okay, so far it does not matter, it could have worked even for analog as well as for digital both. So, once this digital format has permitted me to use another kind of configuration which is equivalent to crossbar but is not a crossbar, we call it a time switch. So, normally 64 kbps, when I am actually going to have a communication link, it can actually have a very high bandwidth. I can use optical fiber, I can use wireless, or even a twisted pair, but the bandwidth is pretty high. So, I can actually transmit much higher number of bits per second. So, it means I can transmit multiple number of voice channels. So, normally if in communication we will actually collect multiple voice signals which are coming at 64 kbps, you will put them together and form a multiplex stream. So, we have E1 carrier system or T1 carrier system in US, E1 is what we use in India. These are multiplexed, time division multiplex streams, voice streams, and they of course means there will be digital thing. If you have a E1 carrier system, it will be requiring, it will be having a frame which is identified by exactly 125 microsecond. So, this 125 microsecond comes because 8000 samples per second have to be generated for a appropriate voice representation. This becomes a kind of a uniform standard in all multiplexing systems, whether it is SDH, E1, T1, everywhere it is 125 microsecond frame duration. Within this I can transmit multiple octets. So, If I transmit 1, 2, 3, 4, 5, 6, 7, or maybe I can put another one, 8 octets in one frame, I am transmitting 8 voice circuits. So 8 voice communication now can be transported over this frame. So I can actually put them, I can get 8 inputs, I am generating 64 or 8 bits every 125 microsecond, putting them in order and then sending it. But now this actually means I have multiplexed, I am sending it, at other end I will just demultiplex and connect back. So the guy who was 1 here, his voice was sample was transmitted in slot 1, it came here, it was taken out, and so on. I can now implement a switching functionality here itself. Okay. If I can somehow have a box here, we will discuss how this will be done, and on this side this frame was available here, I have another frame on this side. So whatever was the octet in the first slot, if I put that octet in third slot here, whatever was octet in second I can put in 8th slot. I can do this kind of shuffling between the voice samples. How this will be done is a different question, but if I can do that, I actually put my voice was here, but it got connected here, it something which was here got connected somewhere here. So in fact in this case, because I have moved, I should draw actually everything as a full example. So let me do this. So again these are 8 slots, so let me do the generate the mapping. So if 1 comes here, 2 comes here, 3 comes here, 4 here, 5, 6, 7 and 8. So what has happened? So one which was coming in here, if this box would not have been there, this would have come out from this one port, 1 prime. But now it is coming at 1, 2, 3 and 4. So it is coming, I should also make it 1, 2, 3, 4, 5, 6, 7, of course I put 8. Yeah. So 1 now is getting connected to 4 prime. If I can actually do this swapping of slots, 1 can get connected to 4 prime, 2 can get connected to, in this case 2 prime, 3 can get connected to 6 prime and so on. So last one, the 8th one will get connected to 5th. So I was able to do switching, and if I can control this map, if I can give a command and say okay the map is going to be changed, I am able to implement something which is known as time switching. Okay. And the advantage is this is like going to be full crossbar, 8 by 8 crossbar. I can actually connect anybody to anybody else. I can even do multicasting, but that multicasting case we are not considering as of now. Okay. And if I create this scenario, this is nothing but can be represented equivalently by a crossbar. 1, 2, 3, 4, 5, 6, 7, 8. So 8 by 8 crossbar. And the which cross points are being snapped in. So 1 was connected to 4 prime. So this cross point is snapped in. 2 is connected to 2 prime. So this cross point is snapped in. 3 is connected to 6 prime. So this is snapped in, and I can build up 1-to-1 equivalence, and both are strictly non-blocking configurations. Okay. So in it I can also build up a 3-stage interconnection network. We will actually come back to that thing at some point of time. Now how you will build up this switch? How you will build up this particular time switch? So, logically if you think, if I can write all this thing into a memory, so if I can write in order, for example, the first byte goes into first location, second one goes into second location, third in third and so on, while I am reading it out, I may not read it in the same order. I may read the sixth location first, second location then seventh, then first and so on. I will be able to achieve this time switching functionality. So, I can use random access memory to create this. So, let us look at how you can actually build up a simple circuit for doing this, a basic time switch. So, I need something called speech memory, SM we call it. So, SM stands for okay, and the voice will be coming into this. Each voice consists of 8 bits. So, 8 parallel wires can actually come, because I have to store a bus has to go, data bus has to go where the data will be stored in this RAM, and RAM normally consists of an address bus, consists of a data bus, consists of a read write control. Okay. So, this I will be doing it through a clock. So, this is a 8 bit bus. I need to generate a frame clock. So, I need to figure out where the frame begins. So, frame clock recovery will be done here. I also need to do the byte clock recovery. In fact, these are now, a byte has been converted to 8 bit parallel system. So, it is a bit clock. So, it is a clock recovery we call it, or word clock I can call it. So, one word is a bit parallel system now. So, the 8 bits are not coming, in this case in even carrier system the highest order bit will come first, then lower order, and the last order will be coming later on and so on. Okay. In this case there will be 8 parallel wires, this is what 8 slash actually indicates. Now, this word clock once I recover, I can give it to a counter. So, this counter will count how many times, if it is a, they are this is not an even frame, I think do not get confused, even consists of 32 slots in 125 microsecond. This was an example. If I am going to use the same exact example here, in fact, yeah, the same exact example. So, this counter will be counting from 0, 1, 2, 3, 4, 5, 6, 7, that is it, and again it has to go back to 0, because frame clock will give a pulse at that time, new frame will start. Okay. So, there will be only 8 pulses which will be generated per 125 microsecond, and this counter can be used to generate the address where you are going to store your word. Okay. So, first slot will be stored in first location, second will be in second location and so on. So, I am going to use a mux here, and this clock, this counter will give you count from 0 to 7 and back to 0. So, it requires 3 buses. Okay. So, and this word clock now can be used to trigger it, and I am going to use a mechanism whereby in a clock, when the clock is high it is going to write, when clock is low it is going to read. Okay. So, I can use that, or I can use the other way around also, it does not matter. Okay. The consequence of this is the word which you are writing in this time slot, it will be read in the same time slot, in same frame. Other way around it will be read later on. For some slots it will be happening, you will be writing now but reading in the next frame. For some you will be writing now itself and reading in the same frame itself. So, this kind of things does happen because as a consequence of this. So, when the word clock, I am actually taking this configuration. So, it has to write, and the address should be used, it will be counter. So, this has to be 1 and this has to be 0, this is the clock which I am putting, and when this clock goes here, this RW bar, so this should become 0 when the write has to happen. So, I have to put a NOT gate here, this is also 3. Now, I have put this line for what purpose? There also has to be read out. there has to be a bus which will be reading 8 bits. The location which has to be read out in the first slot, who will govern this? So, this will be governed by something known as control memory. There is another RAM, there are 2 RAMs basically which are required. Of course, the good thing for us is the input side number of slots per frame and output side number of slots per frame are same. So, life is far simpler in this scenario. I can take this out from the data output from here. I can also write into this will be done so that I can write down whatever you are going to write here will decide the map here. If I want to change the map, I have to just change the values which are stored here. So, in the first slot you are going to read from 6. So, the first location here will be having 6, this 6 will be coming, and during write that 6 will the location will be actually read out in the first slot. So, first slot will be triggered during the read time. In fact, the same clock I should put here. Now, these two will be coming from my control center. So, there is a control unit for a switch which will be sending this command which actually changes this map. So, this is one of the important things. So, when you do a call setup, the call setup is done by actually writing into the control memory. So, in this case when the clock is 1 you are connecting here, when clock is 0 this should get connected here. So, this should be 0 and this should be 1. Okay. So, in this case whenever the clock is high you are writing 1, 2, 3, 4, 5 and this counter is going as an address you are writing in order. Whenever you are actually having the second half of the clock, when it is to read, my clock actually becomes 0 at that time. So, the output of this gets connected and you will read from that location, and this control will be connected to pick up which location. So, it will be finding out the first location. So, this address will be telling in which slot and from where you have to read, that will be given away what is written here. So, during second half when the read is happening you are reading from here, but during first half when you are writing in speech memory, that time your control system also can write into this control memory and henceforth can change the map of this particular switch. This is a very elementary and a basic system, and of course you can also now write down the sizes. This one for example will be requiring how many locations? It is 8 words which will be there. Size of each word will be 8 in this memory. This one will require how many? You only need 3 bits to be stored. So, word size is 3 here, word size is 3 and 8 such words, and you require 8 words here of this thing, word size 3. An important thing is this frame generator will be required, need to be connected to the reset, so that the counter gets reset when a new frame starts. And this is the basic elementary time switch which actually can be used as a crossbar, a simple crossbar. So, if you want to build up a small EPA-BX, a 16 by 16 port for your home or for your office, you can actually use this technique to build it. Of course, you have to build up lot of other stuff for signaling, control, logic and a software also, but this will be the core switch which will be there for a small exchange. Okay. So, this is one of the things which I wanted before I move ahead with the remaining theoretical background, and before moving on to time and space hybrid switches which actually can be built.